Let's talk about proving the equality of sets using informal proof instead of a formal proof by set identities. Set identities work really only well when you are talking about the same base sets that are being manipulated by other operations. But what we want to do, for instance, is take an arbitrary pair of sets and show they're equal. So let's look at an example. Let A be the set of pairs cosine t sine t, where I take t to be a real number between 0 and 2 pi. Or let B be the set of pairs xy, where x squared plus y squared is equal to 1. Now these are both sets inside of the real numbers times the real numbers. So again, they're ordered pairs of real numbers. And I want to show that these things are equal. In order to show that they're equal, I need to show that one set is contained in the other and vice versa. So in order to show equality, the easiest thing is to show that A is a subset of B and B is a subset of A. Which means if I take any element in A, it should also be an element of B. And if I take any element of B, it should also be an element of A. And as you should be predicting, that these are just two different representations of the unit circle, which means that you're going to need to know a little bit of basic trigonometry, which you should know, shouldn't you? So I'm going to let cosine t sine t be an element of A. I need to pick out an arbitrary element, and all I know is that it fits the definition of being an A, which means it's represented as a pair cosine t sine t. But I want to say that if I take cosine t to be x and sine t to be y, then it satisfies the definition from B. Luckily, we have a trigonometric identity that does give us that. Remember that the square of the sine of a t and the square of a cosine of a t is equal to 1. And that means that we can use this to get what we want. This is really not that big of an ideal. It's really just saying I'm applying the Pythagorean theorem to my unit circle, so the triangle I get with the unit circle. So very trivially, we get that we actually do satisfy the conditions for being in B, and therefore A is a subset of B. Now let's prove the other direction. Let's prove that B is a subset of A. So what I can do is let x, y be any element of B, and that means all I know about x and y is that x squared plus y squared is equal to 1. However, this does mean, since I know that x squared and y squared are non-negative, that x squared and y squared are also in most 1. If I take any real number and square it, I will get a non-negative real number. Same with the y. And that means that if I'm taking x squared plus a non-negative number to get 1, it means that I'm actually at most 1, the x squared. And same with the y squared. If I know these bounds on these squares, that also means I know these bounds on the values of the numbers. So that means I know that x is somewhere between -1 and 1, and y is somewhere between -1 and 1. This means I can apply the arc cosine and arc sine functions to x and y. So I have that these ranges are there, so therefore I can apply these arc cosine and arc sine functions to get two numbers t and t prime. If t prime equals t, then I know that the cosine of t is x and the sine of t is y. Otherwise, I have a few things to be worried about, specifically that the arc sine functions and arc cosine functions have different values out, and I need to worry about whether or not which quadrant I'm in, which means I'm going to punt. I'm going to let you figure out the rest of the details for these arc cosines and finish the proof. It's a little bit more work, but I'll let you finish it. I'm going to leave this to you to finish by using technical details about arc cosine and arc sine. For when t and t prime are not the same number, we know something about their range, what numbers they are, and we can use different shifts of them using pi or negative or subtracting them from pi, things like that.